Hi, using this set of coordinate axes and the curve y equals function of x, I'm going to show you how to differentiate. Okay, before I begin, let me explain to you why we differentiate. We differentiate to find the gradient at a particular point on a curve. So let's say this point P over here. We do this because on curves, gradients are different at different points. So, let's say we had a point Q here. You will see that the gradient on this point Q is different to the gradient at the point P. As you can see, these slopes are different. At Q, the slope is much steeper. So, we differentiate to find gradients at particular points on curves. Okay, let's put a point P on this curve once again. And let's give it the coordinates x, function of x. Let's put a point Q on this curve as well. And let's give it the coordinates x plus change in x function of x plus change in x. Next, let's put a chord between the point P and the point Q. Now, this chord has a constant gradient. The slope is constant as it is a straight line. But we're not going to be looking for this gradient. We're going to be looking for the gradient of the tangent at the point P. This is what we want. Now, to get the gradient of the tangent at the point P, this chord PQ is going to have to get smaller and smaller and smaller until its gradient becomes extremely similar to the gradient of the tangent at P. Now, let's talk about gradients for one moment. What equation would we use to find the gradient of this chord right here? Well, we usually say that m equals y2 minus y1 over x2 minus x1. So in this case, m would be function of x plus change in x minus function of x over x plus change in x minus x. And if we simplify this fraction, we get function of x plus change in x minus function of x over change in x. Okay, so considering the coordinates of P and Q, the gradient of the chord PQ is function of x plus change in x minus function of x over change in x. Now, m just stands for gradient, and this is the formula we use to find gradients. So, as I said, the gradient of the chord PQ is this fraction up here. Now, if we want to find the gradient of the tangent line at P, then change in x is going to have to become smaller. As change in x becomes smaller, Q gets closer to P, because the value of y drops as change in x drops. So Q gets closer and closer and closer to P. And if the chord is very, very small, it will have the same gradient of the tangent line at P. So we like to say in mathematics that in the limit as change in x approaches 0, so as it gets very, very small, the function of x plus change in x minus the function of x over change in x equals the derivative of the function of x, or equals the derivative of y with respect to x. So let's imagine for one moment that we're dealing with a curve function of x equals x squared. If function of x equals x squared, function of x plus change in x equals x plus change in x squared. And if we were looking for the derivative of the function of x, we would do this. We would write the derivative of the function of x equals the limit as change in x approaches 0 of the function of x plus change in x minus the function of x over change in x. Now in this case it would be the limit as change in x approaches 0 of x plus change in x squared minus x squared over change in x. And if we simplify this fraction, we get the limit as change in x approaches 0 of x plus change in x multiplied by x plus change in x minus x squared over change in x, which would equal the limit as change in x approaches 0 of x squared plus x multiplied by change in x plus x multiplied by change in x plus change in x squared minus x squared over change in x. Let's get rid of the x squared and the minus x squared at the top of this fraction because they cancel each other out. If we do that, we're left with equals the limit as change in x approaches 0 of 2x multiplied by change in x plus change in x squared over change in x. Simplifying this further, we get to the limit as change in x approaches 0 of change in x multiplied by 2x plus change in x over change in x. We can cancel out the change in x at the top of the fraction and the bottom of the fraction, leaving us with equals the limit as change in x approaches 0 of 2x plus change in x. Now, as you can imagine, this change in x gets very, very close to 0, so we can get rid of it. And if we do that, we're left with 2x. So, if the function of x equals x squared, then the derivative of the function of x equals 2x, which equals the derivative of y with respect to x, in other words. And using the derivative of the function of x, we can find the slope at any point on the curve. We just have to plug the x value into this equation right here, and we get the slope at that particular point on the curve. Well, I've tried to explain quite a difficult concept. I don't know if I've done it well, but if you leave your comments below, I would appreciate it. And thanks for watching.